So work, efficiency, and power. What is the equation for work? Force times displacement, right? And the units for work are joules, okay? Joules, that's a kilogram meter squared per second squared, right? We derived that the other day, right? Okay, and the other thing about the work is that the force and the displacement need to be in the same direction. You gotta always make sure that the force that you're applying is times the direction or the distance that the displacement in that you're pushing it is in the same direction. So we generally, like we already heard this morning, generally don't like to do work. So we try to use things that make work easier for us. Those things are called machines. Most machines you use are complex machines, have a whole bunch of different machines. Okay, but there are 6 identified simple machines. And some of the POE people already know these, I'm pretty sure. Can we list these 6 simple machines without looking? Pulley. Everybody always goes out. That was the first one listed in every single class. Everybody likes that one, I guess. An inclined plane. Yeah, ramp. We know that one, and we're going to use that a lot today. Lever. A screw. Yeah, a screw is actually 2 of those together, right? It's a wheel and axle. There's the other one. I didn't say that one yet. Wheel and axle. That's one simple machine. A wheel with an axle like your steering wheel. Okay. A screw is a wheel and axle, and then there's an inclined plane wrapped around the center pole, right? Okay. So it's actually 2 in 1. And the last one, the one everybody always forgets, wedge, which is really like another inclined plane, right? Except for you're pounding the inclined plane into like a piece of wood or something. Okay, so these are the 6 simple machines, and they help us, they make the work easier for us. Let's put it that way. They make the work easier for us. So the classic example, and so in POE, we go through every single one of these and figure out how to figure out mechanical advantages and all kinds of stuff. And here we're just going to kind of look at the inclined plane mostly. And so if I have an inclined plane, the reason it works as a simple machine is because I have a certain amount of work that I need to get accomplished. For instance, here's one level and here's another level. And I might have some weight, some object, some weight, and I need to get it from this level up to this level. Okay? So there's 2 ways I can do that. I could just do it directly. I could just grab onto it and lift it up to that level, right? How much work, how would you calculate how much work it takes to do that? We have an equation. You take force times distance, right? That's the equation for work, right? Okay, I'm giving everybody a chance to look really awesome on the recording. Okay, so I would take the force times the distance. Now, what would the force be to lift this thing? Yeah, whatever, it'd be whatever the weight of it is, right? I'd have to actually lift it with that weight, counteract that weight, okay? And I would lift it this distance. So it'd be like the height, right? The height. Okay, that is the work that needs to be accomplished, okay? So we're gonna call that the work output. That's the work output. That's what needs to get accomplished, okay? And that might be how I'm gonna do it. So I would take the weight times the height, the force times the distance, or the weight times the height, or so work is force times distance, but I'm going to do a work output. I'm also going to do a work input. Okay. And they're both force times distance. So how am I going to know which force and which distance I'm using? We're going to put little subscripts on the F and the D, so we know. Okay. So work output is always going to be the weight of the object, right? And so we're not going to put in W because that will be confusing, right? So it's a force. What we're going to call it is the resistance force because it's resisting gravity, right? Gravity's trying to pull it down and you're going to try to go against gravity, right? Resistance training, weight training, right, is like usually like springs or something or whatever stretchy things you're trying to resist, right? So this is going to be FR. That's going to stand for your resistance force, which basically means it's the weight of the object. And we're going to lift at a height. The height is a distance, and we're going to put the R on the D also. Okay. So to find the work output of something, you're going to take the resistance force, which is the weight of the object, times how high you lifted, which we're calling the resistance distance. Okay. The distance that we move the resistance. Everybody good so far? That makes sense? Okay. Now, we might not want to do this because if you don't like to do work, that means you don't like to do either that or that, right? Because those are the two parts of work, right? Which one of those things is the reason we don't like to do work? It's the force. That's the thing that's making you tired, right? You're going to apply a force, okay? And you're going to move at a certain distance, okay? The force is what makes you tired. So the problem with this right here is that might be like a piano and I need to lift it up that high, okay? And some of you might not have the potential to be able to actually even exert that amount of force to just lift the piano up, right? So that means you can't do that work. You just can't do it, right? Unless you could figure out a way to get the piano up to this thing and use less force, right? You want to be able to use less force, okay? How can I use less force but still get the same amount of work done to still get the thing up here? If I want to do less force, I would have to do what? I can still get the same W by using less force, but what would I have to do? No, huh? I would have to push it farther, right? I'd have to go a larger distance because, right, so like here's W, here's the exact same W, right? Exact same W. I made them the exact same size. So I could get this W by taking some really big force times a little distance, okay? I get the exact same work by using a little force times a big distance, right? Does that make sense? I can get the same number here. This could be big and that could be small, or this could be small and that could be big, but they still multiply out to the exact same amount of work, okay? So what I can do instead is I can take this object and I can push it up the inclined plane. So here's my force. It's not directly straight up. It's actually at an angle, right? And I could push it how far? Well, I'd push it the entire length of this ramp, right? And I'm going to get to the same place, okay? So the length here is always going to be really bigger than the height of the inclined plane, right? So I can go for a longer distance, which means this force can be less than what it took to lift it up. Does that make sense? Inclined planes help us to do work by lowering our force that we need to use. But we have to apply it over a longer distance. Every one of these six simple machines work that way. Okay, I can use a simple machine to increase the distance that I'm going to have to exert my force, but that will allow the force to be a lot less than what it would normally be. So I'm going to use an inclined plane to push the piano up. Yes, I have to push it a lot farther, okay? Especially if I make this ramp like really, really long. So I probably want to make it really, really long, right? The longer I make that ramp all the way up to wherever I'm trying to get that piano, the less the force it's going to take. Does that make sense? Make it longer and longer and longer, and it's going to be less and less force you'd have to use to push it up, okay? So simple machines lower your force. This is the part of the work that it helps us with. It makes us push it a longer distance, but it allows to lower our force, okay? Now here's the thing, okay? So your work input is right here, right here. This was your work output. This is what gets done. But over here is what you did. Does that make sense? This force times this distance is how much work you put into the thing. The overall accomplishment was it took a weight and it lifted it that high. That's the work output. That's what got accomplished. Here's what you did. You put into it so that you could get that to be accomplished. So your work input is also F times D, right? But we need a different subscript. And the subscript we use is E's. You know what the E stands for? Your what? Effort, right? Right? When you're working in physics, I'm always saying, put in some effort, right? Yeah, so E is effort. So this is your effort force times the effort distance. And on an inclined plane, the height of a ramp, the height of an inclined plane is always then your dr, and your hypotenuse of the inclined plane is your dE. Okay, that's the way it'll always be for an inclined plane, because you're always going to apply your force along this, but your output is actually making that weight go up to here. Okay, so that brings us to what we were trying to do today, efficiency. We want to find efficiency of machines, and it's really easy. It's the amount of work you get out of it, right, divided by the amount of work you put into it. So work out over work in, and then times 100. Put it into a percentage. Okay. Now, here's the part that sometimes I don't think students understand. Efficiencies of machines are always under what number? How efficient can a machine be? Can it be 100% efficient? No, we have friction, we have loss of energy, right? You can never have a 100% efficient machine. That would be called an ideal machine. I guess we could have one on a physics test on a problem. I could say, hey, pretend this is ideal, 100% efficient, which means the work out equals the work in. Okay. But machines aren't anywhere close to that. You can have a 50% efficient machine and that's still pretty good. Okay. Now, if it's always less than 100%, what does that mean? Which one of these numbers is actually the biggest number then? Work out or work in? Work in, right? Now, that's the problem that students have. That means the work out to get this piano is some number, right? Like, I don't know, 100 joules. Okay, that's the work out. That's all the amount of energy you need to lift up the piano up that high. Okay. But this equation then means that when I take my force times the effort the distance I'm going to push it, that I'm going to actually get like 120 joules or something. I'm actually going to do more work than I need to accomplish this. And you always do that. You always do that. Any machine you ever use, and you guys use machines all the time. Okay. Any machine you ever use, you actually put more work into it, okay, than you get out of it. Now, a lot of times some machines are actually using electricity for you, right? But that electricity going into the machine is energy, and so it has to be accounted for. But the amount of work that goes in is always going to be more than the work you get out. Like when I'm pushing up a piano up a ramp. So why would I do it? Why would I use this ramp to push the piano up the inclined plane? If I'm actually going to do more work than it would be just to lift it up. It's a very obvious reason. Because it's about the force. It's all about the force. Because I physically can't lift the piano up that high. So the work's not going to get done, or the work's going to get done. Now I have to do actually more work, right? But I don't really care that I'm doing more work because all it's about is the force, right? So this force over here is less than that force right there, okay? But this distance probably is a whole lot more than this. So when I multiply the smaller force times this big distance, I'm still getting more work that I'm actually going to get out of the thing. And all machines are that way. You put more work in than you get out of a machine, but we're all willing to use it because it lowers the force so much. You understand that? Okay, that's one of your problems. 5/8. 5/8. Write a little explanation down there. If you have to put more work in a machine than you get out, why use the machine? Okay, so work out over work in is your new equation for today. It's your efficiency equation. And of course, that would be FR dr over FE dE times 100. Okay, it's your resistance force times your resistance distance, which basically is your weight times your height. Okay, over how much force you actually put in times the distance that you actually pushed it yourself. All right. Okay, since we're recording today, we're actually going to do these board battle problems. So let's look at 5.7. Everybody got all that down? Okay, let's test your abilities now. And there's a little trick here that someone needs to take a little brain jump for us to figure this problem out. And I want to take that away from you. I want someone to be able to, figure that out and tell me. So let's just look at this problem. It says, what is the efficiency of a 30-degree inclined plane, a ramp? Okay, so we have a ramp. And it's 30 degrees, inclined plane. Okay. If it takes 100 newtons of effort force to push a 120 Newton weight up the incline. Okay, obviously that's why we're using the incline, because we have 120 Newton weight. Here it is right here, 120 Newtons. And the idea is we want to take it from this level up to this level. So we want to take this and we want to raise it all the way up to there. Okay. So I'm going to use an inclined plane, and it says that when I push the thing up instead, I'm only using how much force? 100. So obviously that's why I want to use this, because I don't have to use 120 newtons. I can just use 100 newtons. Okay. So it's asking for the efficiency. So we just have a new equation. Efficiency equals FR dr over FE dE. And what is the resistance force? What is the weight? It's 120 newtons. So I'm going to put 120 in for that. Okay. What is the dr? Well, it wasn't given, right? Okay, but where is it? Where is the dr? It's how far I'm going to lift this up, right? So it's the height of this inclined plane, right? So I can label that height there dr. Okay, but they didn't give it to us. So I'm just gonna leave it dr. Okay, over the effort force. How much effort force did we use? 100 newtons. Okay, 100 times the effort distance. Did they give that to us? They did not. They didn't give that to us either. Where is it on the inclined plane? Yeah, it's the hypotenuse. We always push along here, right? So there's the dE. Okay. And I'll label it. There it is, dE. Okay. So they gave us neither of these things. That's not good. When we have an equation and you do your little inventories, right? It's always bad if you try to have an equation that has two unknowns in it. It's like, what's happening here, right? So this is the point in this. I like this problem because usually we board battle this problem and people work on it and they go, I don't have dr, I don't have dE, and then they curl up in the fetal position and start crying and say, I just give up on life. It's always funny to watch that happen. Okay, so we're not going to do that because obviously I gave you a problem that we can solve. So we got to think about it. Use your brains. Think about stuff that you know. Okay, I don't know dr and I don't know dE. Is there any way to solve this problem? No, I don't have any numbers. I don't have any numbers for these sides, but I do have an angle. Multiply what by sine 30? multiply dr over dE by sine 30? Why? Okay. Did that make sense? Did you hear what I was saying? I don't know dr and I don't know dE. But I know the relationship between those two sides because I have an angle. Trig functions are relationships between two sides of a triangle. That's what they are. Sine, cosine, tangent, right? If you wrote those all out, what are you doing? You're taking one side divided by another side of the triangle, right? All those three trig functions is a side of a triangle divided by another side of the triangle. Correct? Sine of this angle, sine of theta, is opposite over hypotenuse. And in this triangle, that would mean this side, dr, over dE, right? So instead of this dr over dE, right there, instead of this, I could put in this. Right? Good job, Luke. So in dr over dE, I could just put in sine of 30. I wasn't given either side, but I was given the angle. 120 divided by 100 is 1.2, right? Everybody knows what the sine of 30 is, right? 1/2, right? I use it all the time, right? 1/2. So 1/2 of 1.2, 1.2 divided by 2 is what? 0.6. And of course is a efficiency. So times 100% gives us 60%. 60% efficient. We could figure it out and we didn't actually even need the dr or the dE. So we just learned something. So let's not forget it. Let's try to apply it. So let's do another problem. 5.9. A crate is pulled up a 15-degree inclined plane, pulled up at constant velocity. Okay. If mu equals 0.16, mu equals 0.16, what is the efficiency of the inclined plane? Wow. That was all we're given this time. We're not even given the forces this time. I have no idea what kind of weight we're lifting or whatever. So what do we do when that happens? We just start writing the efficiency equation out and seeing where it takes us. Obviously, we can figure it out. We must not need all those things, right? So we don't just quit. We get excited like, ooh, this is going to be awesome. Where are all these things going to go away? How's this going to work? It's very exciting, right? That's the level of first period excitement. Efficiency is FR dr over FE dE equals, okay. All right, how am I going to get my FE? Well, what's my F? Let's do FR, I guess, first. What's FR? What force? What? No, FR is the what? It's simple. It's not, don't get complicated here. What's the FR? It's the weight of the object, right? It's always the weight of the object. It's over here. It's what you're trying to lift, right? Okay. All right. I'll tell you when I ask a hard one. Okay. So the FR is weight, right? So I'll put in I don't know. Can I put in W? Is that okay? Okay. That's not work. That's just the weight of the object. Times dr. Dr was not given. Here's dr. Here's dE. Right? Neither of them are given. Yeah, instead of that ratio, I could actually put in sine of 15, right? Okay, so I'm going to just, so over on top of here, I have weight. Down here, I have FE, which I don't know what that is yet. And then instead of the dr, dE, I'll just do times sine 15. Okay. All right, what can I put in for FE? Well, I need to probably draw an FBD. Was that our least favorite unit or something? Oh, yeah. Okay. FBDs aren't that hard. How do you draw it? What do you do? What do you do with the weight of an object on an inclined plane? What do you do? It usually goes straight down, but we don't do it that way. What do? Yeah, we do components. So we do one coming in like this, and we do one coming down like this, right? We split it up, perpendicular and parallel. And do you remember what they each are? This one here, mg, or weight cosine, right? This is weight cosine theta. So we were board battling these the other day, and there were a couple people that turned these around. So that's not good. Okay. And this one here is weight sine theta. Okay. I got a normal force coming this way, right? It says that I'm pulling this up the inclined plane. So I'm have an arrow like this, which actually is my FE, right? That's what I'm pulling with, right? That's what I need to put down in here, right? We have one more force we're missing. Friction. Which way should it go? Huh? Yeah, down, because I'm pulling up, right? So friction just always goes opposite whichever way you're going. So you got to know that, and then you put the friction the other way. So I'm going to put another one down, and that's friction. And who remembers the equation for friction? Mu Fn. And what's Fn? Yeah, Fn would have to equal this one because they're not accelerating this way either, right? Okay, I think you guys know this stuff. So Fn is W cosine theta. So instead of this Fn right here, I could do mu W cosine theta. Does that make sense? So then what am I, so I'm trying to figure stuff out here. I thought the weight is my FR. My weight is my FR. And FE, what would I put in for this FE here? What would it have to be equal to? It's constant velocity going up the inclined plane, so that means forces are equal. So this would equal both of those, right? This one would have to equal both of those things to be balanced. So on the bottom, I could put mu W cosine theta plus W sine theta. Okay. You see now, you have an aha moment. What happens to the weight? It's in up here, and it's also in both of the terms in the bottom, right? So that's why I can cancel it. If it was only in one of the term, I couldn't cancel it. But it's in both the terms, so I can cancel the weight out of all of those. So on top, there could be a sine 15, right? I can move that on top, right? Yeah, there's a 1 there, but times sine 15. So I could do sine, in fact, I'm just going to keep theta, sine of theta over mu cosine theta plus sine theta, right? That should be it, right? And times 100, that should be my efficiency. So all I needed really was the angle and mu. That was it. That's why I didn't give you anything else, because you could solve it, right? And it's cool, I think. So I don't think I have this. We just derived this equation. I don't think I have it on a sheet anywhere, in a book or anywhere or something. But technically, that would be the efficiency of an inclined plane. I mean, that would be it. That'd be the efficiency of an inclined plane in any inclined plane, right? So because it has mu in there, it has the angle in there. It doesn't really matter what the forces are, okay? Because they all cancel out there. Yeah. 63%. Okay. 63% would be the answer for that. All right, last thing we're going to talk about today is power. Power. So we have a lot of things that are rates. We've talked about a lot of things this year that are rates. So if you're going to move a certain displacement in a rate, that's like, rates mean over time, right? Over time. So d over t was a rate change of displacement, and that was called velocity. And then we talked about, hey, changing your velocity over time. How fast can you change your actual velocity over time? And that was called acceleration. So we can have a rate of how fast you can do work. Some of you, a lot of you do the ELAB, 100% of the ELAB. Some of you do the 100% of the ELAB in a much shorter time. You're a more powerful student. Okay, you do it faster. That's who we want to hire for a job, right? I can hire a whole bunch of people that can actually do the work, but I would like to hire someone that can do the work in half the time, right? We try to hire power, right? Manpower or woman power, right? That's what we want. Okay, so what's the equation for power? It's pretty easy. It's the rate of how fast you do work. So it's work over time. Catch that? Catch that one? Work overtime. You want to hire people that would do work overtime, like to work overtime. Yep. Jokes are going to get better. Trust me. So work over time, that would be F times D over time, right? And so this is interesting because what's D over T? D over T is a velocity, right? So an actual equation for power that I could also use would be force times velocity. Okay. Now there was a good question in the other class. They said, well, if it's going at a constant velocity, how can there be a force? This isn't a net force. This is just the force that you're pushing on it. So if I'm pushing this object with a certain force, okay, and it's moving along at a constant velocity while I'm doing that, that's not a net force. The forces are balanced. There's friction that's balancing out whatever force I am, but that's not what we're talking about. I'm just talking about what force am I applying to it? My effort force, right? In the inclined plane problem, we had effort force and there was friction that balanced it out, but there was still an effort force, right? So it's the effort force times whatever the constant velocity is, and that would be the power. So what are the MKS units for power? MKS units for power. You can use this equation right here to figure it out. MKS. I'm not talking about the derived unit, MKS. Okay, well, first of all, what's a force? It's a Newton, but that's a derived. So what's the MKS for force? Per second squared, right? That's a Newton, right? A mass times acceleration, right? Okay. And then we're going to take it times a D. So that's what's the unit for distance? Meters. So that's going to make this a meter squared, right? Okay. And that was work, right? That was work. That's what we got for work. Now what are we doing? We're taking work and we're dividing it by time, and time is in seconds. So seconds cubed. Very good. Kilogram meters squared per second cubed. So this is complicated. So we have to have a derived unit. What is the derived unit for power? What is the derived unit for power? Hey, Jeff, what are the derived units for power? Come on, guys, you know it's fun, right? It's fun. What is the derived units for power? I did. I said it 3 times now. No, what's not on second? What is the derived unit for power? The always funny thing about this joke is there's a whole bunch of people that still haven't got it. Okay, we'll let you in on it. Actually, I just wrote it. It's such a funny joke. I actually just wrote it right in the book. I'm just like not even being, what are the units for power? Exactly. That's the answer. Watt. Watt. Never gets old. Never gets old. Even after you've heard it probably 3 times in 3 different classes, it never gets old. Just ask all these people here. So I'll use the joke again because I love it, and I'll just keep on saying it over and over again for like the next couple units. So now you're in on the joke. So the answer, when I say, what are the units for power? You say, exactly, or yes, or that's correct, Mr. Herman, right? And then everybody else, that doesn't know, they're like so confused, and we can laugh at them. Talking to my kids last night, and I said, my students, they don't laugh at my jokes. They don't think I'm funny. And they're like, what? Oh, Dad, you're hilarious. They couldn't believe it. They thought, man, it's just like nonstop laughter at home. Okay. All right. I thought maybe I was like the only cool parent, in the world. Okay. So if you're still not with us, the derived unit for power is watts. Okay? Watts. A kgm squared per s cubed is called a watt. Now, it used to be that the main source of power in America was the horse, right? So we had a horse, and so they did a whole bunch of testing with the horse. Hey, I got 4 legs though. Last class I had like 6, so that's better. Okay? And they did testing with horses, and they found out that an average horse could lift 750 newtons of weight. They could lift it 1 meter. There's 1 meter, and it took them how long to lift it 1 meter? It took 1 second. So 750 newtons times 1 meter divided by 1 second is 750 watts. That's an average horse. It was a tragic thing. There was some below average horses, and they just got pulled off the cliff and died. It was okay, but eventually they figured out, hey, the average horse can do 750 newtons 1 meter in 1 second. So 1 horsepower is 750 watts. Okay, the horsepower is big. It's big. That's a lot of watts. Okay, 750 watts. So I might ask you somewhere along the line to, how many horsepower is this? Okay. All right. Whenever we have new translational equations, we also know that now, since the last unit, there is also a rotational world, right? So I can go and I can do a lot of work on that chair, rotating it in a certain amount of time. So there's an equation for rotational power also, and you should be getting good at this. Instead of these symbols, we use what? Instead of a force applying directly on an object, we need to do what to rotate something? Torque, right? It's still a force, but it's a force times an R, right? So instead of an F, we put in a torque. And instead of the D, instead of a linear displacement, we're going to have a rotational displacement. And what's the symbol for that? The egg, right? In radians over time. Torque egg over time would be the rotational power. But what is egg over time? Yeah, but. So power equals torque but. Torque but. I tried to make a really funny joke in the other class, but I'm too much of a boomer, so I didn't really understand the word. And I thought everybody was going to laugh at torque butt because I thought that's what you call that dance or something, torque. That's what I found out. Yeah, so my joke, no one got it because I just not, jiggy witted enough. So you can just, my boomerish came through, and it was like such a tragic moment in my lecture. I was like, oh, it's gonna be so good. They're gonna love this one. torque butt, you know, and then I'll get it. And then I realized that that's not what the word, I thought the word was always torque, whatever you're doing or something. So it's power equals, was it? Torque? Power equals torque butt. Torque butt. See, I should have wrote that down when they told me, and then I could have said power equals torque butt, and you guys would have laughed. This is all on my recording on Zoom. That's great. Might have to do some editing. Oh, so you laugh at that. Yeah, it's funny. That's funny. Yeah. Okay. All right, we got one more problem, and then we're done for spring break. Okay. Let's see. 5:10. Here we go. Ready? A person drives their car up a parking ramp 12 meters high. 12 meters high at a constant velocity in 20 seconds. The mass of the car is 1.50 metric tons. Calculate the power output of the car's engine during this time in horsepower. So that's good they did output, because input would have been harder, because I don't know how much of incline they went all the way up, you know. Output's easy, right? Power output is work output over time, and work output is FR times DR, right? Over time. The time was 20 seconds. The DR is your height, right? How far up in the air did the car get eventually? What was it? 12 meters, right? So in for the DR, I can put 12. And FR is the weight of the car, the weight of the car. How much does the car weigh? I threw in a little extra thing here because I thought maybe people wouldn't know about this. So I thought it'd be extra learning for fun. Yeah, what is a metric ton? Anybody know? Anybody know what a ton is? A ton is 2,000 pounds. 1 ton is 2,000 pounds. Okay, so what is 1 metric ton? Okay. What? 1 ton equals, I should put an equals in there. 1 ton equals 2,000 pounds. What is a metric ton? Well, here's the deal. A kilogram of mass, okay, is around 2.2 pounds. Okay, a kilogram of mass is around 2.2 pounds. So a metric ton is actually a mass. Instead of a weight, it's actually a mass. It would be, a metric ton is actually equal to 1,000 kilograms. Okay. Technically, another word for a metric ton would be, no, use the metric system. Use the metric system. I didn't even talk about this the other day. It's 1,000 kilograms, so a what? It'd be a megagram, technically, yeah. A megagram is the same thing as a metric ton. Why do they use the word ton? Because 1,000 kilograms, or 1 kilogram is like 2.2 pounds. So 1,000 kilograms is equal to a weight in pounds is like 2,200 pounds. That's why they call it a ton, because it's close to it. Okay, but a metric ton is actually bigger than a regular ton by 200 pounds. Okay, anyway, metric ton is 1,000 kilograms. Okay, thought you'd like to know that information. A megagram. Okay. So this says 1.5 metric tons, which means it's how many kilograms? 1,500, right? So we need to do what with that? Because we want the weight. 1,500 kilograms times 9.81. Okay. We got 14,715 newtons times 12 divided by 20. Times 12 divided by 20, and we get a lot of what? Yes, we get a lot of what? We get 8,829 watts. 8,829, but I don't think that's what we're supposed to put the answer in, right? It says put in horsepower. So what do I have to do with that? I gotta divide by 750, right? I can put another 750 on the bottom there. So divide by 750, and it looks like 11.8 horsepower. 11.8 horsepower. That's how much power it was. Okay. Everybody good?